Okay, so we're going to talk about heat transfer and heat transfer methods. There's many different examples of heat being transferred. We have um, under in the earth, we have some molten lava there. We have some hot regions there, and we have radiation coming from the sun. We have somebody dressed in layers on a certain day to try to stay warm. There's all sorts of different things that we'll talk about with heat being transferred from one place to another. Now, part of understanding heat transfer and understanding energy and forces and pressure and momentum is going to deal with the kinetic theory of gases. So let's just flesh this out right now. In the kinetic theory of gases, we're going to say that the particles are in constant random motion, that they collide with each other and with the walls of the container, that each collision changes the particle's speed. So as a result, the atoms and molecules have different speeds. We have this container, this four-walled container with a bunch of gas particles in it, and they're all bouncing around in there like crazy. That's how we start off our discussion of the kinetic theory of gases. And when we do that, we have this distribution of speeds in there. It turns out that at 300 Kelvin, relatively, normal temperature, we would have the most probable speed of a gas molecule in there to be 400 meters per second, but it would have a range of speeds from fairly low to speeds very fast, 1,000 meters per second. Some of them will have that speed. Now, when we increase the temperature by fourfold from 300 Kelvin to 1200 Kelvin, we're still going to have some of the gas molecules have these relatively small speeds, and we'll have the distribution increase. So fourfold increase in temperature, we have a twofold increase in the most probable speed, and we have this wider distribution of speeds at the higher temperature. That's what goes on with molecular speeds and this kinetic theory of gases. Kinetic, the motion, the kinetic energy of these gas molecules. So the way that this is derived is pretty neat, because we're jumping back into physics 1. We're talking about net force equals mass times acceleration, right? That's Newton's second law. That's really fundamental to how we've been dealing with things. And what we can say with using Newton's second law here is, all right, so mass times acceleration. Acceleration is the change in velocity over the change in time. So mass times the change in velocity is delta mv, the change in momentum. I remember that from physics 1, divided by time. All right, so the average force, net force, the average force that a single particle will exert on the wall of this container is going to be the difference between the final momentum and the initial momentum. So this thing's going to slam into the wall and bounce off again. So it's final momentum minus initial momentum. And then if we're going to keep track of this over time, we'll say, okay, and that'll be divided by the time between successive collisions. So if I keep slamming into a door to try and open it, my average force will be the change in my momentum. And then if I keep doing it repeatedly in order to get the average value, I'll figure out the time between each time I slam into the door. So in this case, this particle is going to bounce into this wall and then travel all the way over to the other side and back again. Well, if velocity is one of the things that we know or think we know, or something that we're hanging our hat on here, then we'll say, all right, so the time between collisions, since velocity equals distance over time, time equals distance over velocity. So the distance is 2 times the length of this container, because we're only interested in one wall right now. So the length of this container is going to travel, bang, hit the wall, all the way over the other side and back again. So 2 times the length divided by the velocity is a unit for time. Now the reason that we did that, because that's stupid, right? The reason that we did that is because this velocity jumps up to the numerator and we get this mv squared, and that looks very familiar to me. That gives me the idea that we'll build up to something with kinetic energy if I have some mv squared going on. So that's why we're doing it that way. We're deriving an equation here, so just be patient. Just let this happen. So for a single molecule, the average force is mv squared over L. Well, we don't have a single molecule. We have a whole bunch of molecules. Capital N stands for the number of molecules. There's a whole bunch of them. And since this is going on in 3-dimensional space, we only have 1/3 of the molecules accounted for if we're doing just the x-axis. Equals mv squared over L. This squared with the bar over it, we're not talking about the average force really, we're talking about the root mean squared, well, not at average speed, we're talking about the root mean squared speed. Alright, so pressure then, remember from earlier in this course, is force over area. We've just come up with this equation, this derivation for what force is, divided by L squared. So N over 3 equals mv squared over L cubed. That's the volume. Alright, so now we'll jump back to the gas law from the last chapter and say, alright, so PV, pressure times volume, equals nKT. So we have pressure and volume here, and multiply both sides by volume, and we have 1/3 N mv squared equals nKT. So now I have 1/3 times mv squared, so I can come up with an equivalent expression if I wanted to have this be 1/2 mv squared. Why would I want that? Well, because that's kinetic energy, right? So if I want that to be 1/2 mv squared, then I'll change this coefficient to be 2/3. So kinetic energy equals 1/2 mv squared, that's a root mean squared velocity, which it turns out is equal to 3/2 kT. Everything else cancels out. We simplify this. Now this is a big deal because we've just said that the average kinetic energy of a gas molecule inside a container is proportional to the absolute temperature T in Kelvin. And we even have a specific, with coefficients, 3/2 kT. K is Boltzmann's constant. 3/2 kT. We have this value for the average kinetic energy of gas molecules. That's important to us. It's going to be important coming up soon because we're going to harness that energy to do work for us. And now we have an expression to describe that energy. It's pretty cool. You can do all sorts of calculations just with what we have right here. So 1/2 mv squared is the average kinetic energy, or root mean squared kinetic energy, equals 3/2 kT. So what is the velocity? So this is somewhere around body temperature, I hope. So air is a mixture of nitrogen and oxygen molecules. If they each behave as an ideal gas, determine the root mean squared speeds of nitrogen and oxygen molecules when the temperature of air is 293 K. So we can figure out the speed of those molecules. So for nitrogen, the speed, we get the mass, we have root mean squared velocity is square root of 3 kT over the mass, so the square root of 3 times K, K is 1.38 times 10 to the negative 23rd joules per Kelvin, times the temperature of 293 Kelvin, divided by the mass of nitrogen molecule, and we get 511 meters per second. So that's wicked fast. And again, that would go back to our Boltzmann distribution, so it's a little bit smaller than the 300K value. But that's the most probable speed, which isn't the same as the root mean squared speed on here. Root mean squared would be slightly different, but so you get a sense of the root mean squared velocity of a nitrogen molecule. All right, so this brings us to this other concept then, that gas molecules, just by virtue of being at some temperature above absolute zero, have energy. We're talking about that in terms of kinetic energy right now, but we're going to more generally speak of it as internal energy. So we've used sometimes as an indicator of potential energy. Here it's kind of in that same context. We're going to call that internal energy. And so internal energy, now not just for the average or an individual molecule, but for a whole bunch of molecules. So N, capital N, is the actual number of particles, 3 halves kT, or if we want to do it in terms of moles, 3 halves nRT is the internal energy. So if I tell you I have, I don't know, 12 moles of nitrogen gas at a temperature of 400 Kelvin, you could figure out the internal energy of that collection of nitrogen gas molecules. All right. This idea that particles, so we're talking about gas particles, we're going to jump into liquids and this phase equilibrium just for a moment here. If I have a liquid, so a bunch of molecules of some liquid, maybe this is water since that's something that we're pretty familiar with, some of those particles have high energy. At whatever temperature, we have this distribution of energies over that range, and some of those liquid molecules have the ability to jump from the liquid phase into the gas phase, just because they're moving that quickly. So some of those will jump from the liquid phase into the gas phase. And some of those gas phase molecules will have a distribution of speeds and temperatures, and some of them will be pretty low, and therefore they will jump back into the liquid phase. So eventually you reach equilibrium. Now this is a sealed container with vacuum above it initially, so we get what we call a vapor pressure above the liquid. Some of that liquid is in the gas phase, providing a layer of pressure above the liquid. If I have a glass of water sitting on my kitchen table and I leave it there for a week, some of that water will disappear. It doesn't boil off from the liquid phase into the gas phase. I don't sit there and stare at it and see it boiling. What happens is that some of those liquid molecules at room temperature have enough energy to jump into the gas phase. That glass of water on my kitchen table does not have a cover on it, and it's not a sealed vessel with no way for the gas phase water molecules to escape. So they do. A little gentle breeze will blow some of those molecules away from on top of the liquid water, and they will just either make my kitchen air a little more humid, or I don't know, I'll breathe them in, something. So they will jump into the gas phase and they won't go back into the liquid phase, and so there'll be less liquid water inside that glass of water, and eventually it will empty out, it will evaporate. If we do get something to boil, that means that we've increased the temperature to a point that the vapor pressure equals the outside atmospheric pressure. So what happens when I boil a pot of water on my stove is I've increased the temperature to the point that those liquid molecules are jumping into the gas phase equal to what the atmospheric pressure is in my kitchen, which we're at about sea level, so it's about 1 atmosphere of pressure, or 1.013 times 10 to the 5th pascals, so 100 kilopascals is pretty good estimation of that. So water at 100 degrees Celsius will intersect with the atmospheric pressure. Now, if you've ever heard of, you go mountain climbing, or somebody who lives at a high altitude, and you look at the, I don't know, box of brownies you have or something, sometimes they have a high altitude cooking instructions, a different recipe, because it turns out if you're at the top of a tall mountain and you want to make some spaghetti, you boil the water and you dump the spaghetti in, and it may never cook and soften because it's boiling at 90 degrees, not 100 degrees. So it either takes longer or winds up being impossible. If you want to cook something even faster, you can get a pressure cooker. What happens with a pressure cooker? Well, that increases the external pressure, maybe doubles it, and therefore things will boil at a higher temperature. If something boils at a higher temperature, then the stuff inside it is cooking at a higher temperature, so it doesn't take as long to cook. That's also colligative properties. If you add salt to your water, you change the boiling point of that water. That water then boils at a higher temperature, therefore it would cook your, I'm always cooking pasta, I guess you'll cook your pasta faster because you're cooking it at a higher temperature. If I want to cook pasta in regular water, it's going to take a specific amount of time to cook because that water is at a constant 100 degrees Celsius. Boiling it longer doesn't increase the temperature of the water, it just causes the water to jump into the gas phase. Steam is hotter than boiling water, but boiling water is at a constant 100 degrees Celsius. All right. Turns out that pressure and temperature have an effect on the phase of something. So if we're talking about water ice, we have a case where at particular temperatures and pressures we might be able to have a triple point where solid, liquid, and gas can all coexist. But generally what happens if we're at a certain pressure, so let's just kind of pick a pressure up here somewhere, and I increase the temperature from wicked cold, I have solid ice, wicked cold, solid ice, wicked cold, solid ice, wicked cold, solid ice, and then I get to a point where the temperature is at 0 degrees Celsius at atmospheric pressure, and by adding more heat I will go from a solid to a liquid. When I do that, I will then have liquid water, and I'll have liquid water for a while, increase the temperature, liquid, 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 increase the temperature, and then finally I'll go from a liquid to a gas. And that's how I would do that. At a given pressure, I could look at what goes on there. Now, I could also have a case where at constant temperature, but really low pressure, maybe I'd have gaseous water, water vapor, but then if I increased the pressure at that temperature, I would turn into liquid water. And so you can look at some different things that go on with a phase diagram, which would tell you what's going on. All right. Fusion and other things. We don't need to do too much with that. I guess I didn't mention this specifically, but so I have my glass of water that's evaporating on my kitchen table, but if I go to, I don't know, an amusement park and I'm sweating and having a miserable day because it's so blazing hot outside, They'll have a mist tent or somewhere where they'll splash water on your face. And that really cools you down. Why does that cool you down? Why do you sweat in the first place? Well, here's the thing, that when you have this layer of water on you, some of those water molecules will be really high energy. Those high energy water molecules will jump into the gas phase and go away. When they do that, the remainder of the water will equilibrate back to that distribution of temperatures, meaning that it needs to take energy from somewhere. How about you, to redistribute its energy. So you lose some heat to the water. The water then loses its high energy molecules to the gas phase, and you lose more heat into the water, bringing it back into its equilibrium. So that's how you cool down when you sweat or walk into a mist tent. Talked about this a little bit already. So now the transfer of heat. This is largely conceptual. We have a couple of equations that we'll deal with here. But convection heating, convection ovens, heating by convection. Convection is the process in which heat is carried from one place to another by the bulk movement of a fluid. So when you boil water on your stove and you dip your finger just into the topmost layer of water molecules, it still burns, it still hurts, because it's not just the water that's in contact with the hot bottom where the burner is that warms up. It all warms up because these water molecules right here at the bottom will heat up. They will become less dense by virtue of heating up, and they will rise. Heat rises. Remember that idea? And the cold water molecules at the top will sink down because they're more dense, because they don't have as much energy. They're not wiggling around, spreading out. And so that goes on. I think I have... Here's conventional convection heating. So generally you have baseboard heaters in your house. Those will heat up the air molecules around them. Those hot air molecules become a little less dense and rise. And then you have the cold air molecules from up at the top sink down, come in contact with the heater, and go up again. Honest to goodness, people, I bought a condominium when I first moved to Salem, Massachusetts, that had ceiling electric. When I turned on the heat, the ceiling to my place got warm. Now you can imagine how dumb this is, right? Like, my wife thought she had a relapse of malaria, because you're standing there in the middle of winter, you're freezing, your feet are freezing, you turn on the heat, and the ceiling gets hot. Well, the cold air stays on the floor, your feet are still freezing, and your head feels hot. It's really dumb. It goes against physics, people. So that's how convection works, is that you heat something up, it becomes less dense, it moves up. The bulk flow of molecules, the bulk flow of air molecules or water molecules, whatever. You ever meet those people that have the freezer on the bottom and the fridge area on the top in their refrigerator? Well, that makes sense, doesn't it? Because you'd want the coolest part to be at the bottom and the warmer part to be at the top. I have side by side myself, but there's different things you can do. This happens on Earth as well. Ground level tends to be pretty warm, either by way of asphalt or dark grass. It absorbs solar radiation and heats up. When that heats up, then we have the idea that we'll have a convection, a thermal current going on, where the warm ground, the air rises up to cooler areas. And I guess if you're a glider pilot, you can gain altitude that way. We can have forced convection in our automobiles to cool down the cylinders. We can force the cool liquid to go around and the hot fluid to come out and keep things at a regulated temperature. All right, so we'll set aside convection for the moment. Convection, conduction, and radiation. Conduction is the process where heat is transferred directly through a material without any bulk motion of the material. One mechanism for conduction occurs when atoms or molecules in a hotter part of the material vibrate or move with greater energy than those in the cooler part, and those energetic collisions pass along the energy to their neighbors. Materials that conduct heat well are called thermal conductors, and those that conduct heat poorly are called thermal insulators. If you've ever roasted marshmallows over a campfire, sometimes you'll use a stick, and so you put your marshmallow on that stick and hold it in the fire, and you roast your marshmallow, and life is good. And sometimes there's these kind of longer metal forks that you might use that are more reliable. You can find those easier than sticks. And when you do that, sometimes you'll notice that when you have one end of the metal fork in the fire, the other end in your hand gets warm because metal is a good thermal conductor. Maybe you go to a sporting event and you sit outside in the cold on metal bleachers, and you sit down on the bleacher and you feel cold coming up through you. That's because metal is a good thermal conductor, and it's conducting heat away from your body. And then you're smart and you bring a blanket to sit on, and when you do that, the blanket is a good thermal insulator. It keeps the heat from flowing through you so well. With conduction, we have this equation that we're building up to here. The conduction is the flow of heat directly through a physical material. So we have a metal bar here, I guess, for lack of a better example. We have two different temperatures, T1 and T2. Heat will flow because there is a temperature difference. If everything is at the same temperature, then there's no reason for heat to flow. And we have the length, the distance that it will travel through. So we'll find that the amount of heat that flows through the rod increases if we increase the cross-sectional area. If you have a thicker rod here, then more heat will flow through there. You have a bigger pipe. Think of it like water flow or something. If you have a thicker pipe, then more water can flow through it. It will increase proportionally to the temperature difference from one end to the other. So if everything's at the same temperature, no heat will flow. If you have a huge temperature difference, then more heat will flow. And it will increase steadily with time. Well, we'll have the more time, the more heat will flow. And it decreases with the length of the rod. So if the rod is longer, you'll have less heat flow. Again, kind of like a pipe analogy. So here's another image of it, but we'll get to the equation here. So heat conducted during a time t through a bar of length L and cross-sectional area A is Q equals K, lowercase k, this is the thermal conductivity constant, A delta T over L. Thermal conductivity will be for a unique material, so the aluminum bleachers that you sit on at the football game has a different conductivity value than the woolen blanket that you sit on. Glass windows versus triple pane vacuum insulated windows will have different thermal conductivity constants. So here's one list of thermal conductivity values. Aluminum has a high thermal conductivity. It will conduct a lot of heat. Copper silver, all high values of thermal conductivity, whereas things like air, if you wear if you dress in layers in the winter time, you're dressing in layers in order to trap pockets of air. Air is a really bad conductor of heat. It's a good insulator, so that will help you stay warmer. And so we have a range of thermal conductivity values here. If you ever see insulation in your house, what insulation is this material, either like fiberglass or like foam material, that has these little pockets of air cut inside them, trapped inside them, trapped air spaces, and that makes it a good thermal insulator. So heat flow by conduction, Q equals Ka delta T over L times time. The other way that we'll rearrange this equation sometimes, if we're talking about the rate of heat flow, that's Q divided by T. So I'll just divide both sides of the equation by time. Q over T is joules per second. That's watts. Watts of power that would be involved in heat flow, how much power you're losing from your house by having an uninsulated window or something. You can figure out the thermal conductivity of that window, the area of that window, the thickness of that window, and then you'd have to do this for a specific day. Hey, it's negative 5 degrees Celsius outside and I want to keep my house at 20 degrees Celsius. So you have a delta T to think about there. All right. So here's a window, rate of heat loss. We could figure that out if we wanted to. We don't want to right now. So a couple of examples for you. Okay. Conduction, convection, and radiation. Also in the realm of convection, since we live here in Salem, Massachusetts, we can appreciate that there's sometimes a breeze that comes off of the water. It turns out in the daytime, solar radiation is absorbed more by the land, where things tend to be darker and absorb solar radiation more, which we'll talk about when we talk about radiation coming up. Heat rises, those air molecules rise, creating a relative vacuum. We're not suffocating, but relative vacuum that's filled in by the air molecules that are sitting over the ocean. The ocean is largely at the same temperature, which is cooler than a bright sunny day would be here on land. So that we get a cooling sea breeze during the day. Now at night, then, the ocean loses infrared radiation, loses heat energy to the atmosphere more efficiently than land does. And so at night, as you're sitting on the shore, you get a warm breeze from the land as the land air tends to fill in what is being lost above the ocean. So that's a cool thing. All right, radiation. Hey, you know what happens? You turn on that electric burner on your stove and it glows red hot after a little while. Well, if you let it keep glowing, it would go red, orange, yellow, green, blue. It would go through these steps. Red, yellow, white, blue, I guess. Objects at body temperature radiate infrared, which you can see with night vision binoculars. So this is what happens with radiation. Everything above absolute zero will radiate energy in the form of electromagnetic waves. So the amount of energy radiated by an object due to its temperature is proportional to its surface area and also the fourth power of the temperature. You can do squared twice if you don't have a y to the x button on your calculator to do to the fourth power. But think of it, we're talking about really big numbers. If we're talking about 300 Kelvin, and then we raise that 300 to the fourth power, we're jumping into some really huge numbers. Now the other piece to radiation, radiative heat loss, is emissivity. And this is a number between 0 and 1 that indicates how effective a radiator an object is. A perfect radiator would have an emissivity of 1. The easiest way to think about this is a black car parked in a hot parking lot. That black car would have an emissivity value close to 1. It's a good absorber of radiation, and it's also a good emitter of radiation. So that black car parked in the sunny parking lot will absorb a lot of solar radiation. It will heat up a lot, and then when you touch it, you feel pain. You feel that heat coming off. Whereas a white car or a more reflective surface isn't a good absorber of radiation, neither is it a good emitter of radiation. So we want to talk about radiated power. So remember when we did conductivity, we did Q over T, and that gave us power in watts. Now we're doing another version of power in watts. It's the emissivity value, so a number between 0 and 1. We'd have to tell you something there. Usually, we'll pretend this is a perfect absorber, so you just use 1. Sigma, which is the Stefan Boltzmann constant. It's a really tiny number. It better be, because we're doing T to the fourth power. If we're going to have any sane numbers, we better have a small constant here. So this is just a constant. Area, the surface area of the object. So if I have my car parked in the sun, then the surface area that is exposed to the sun of my car times temperature to the fourth power would tell me the radiated power for my car in that condition. So radiation is the process in which energy is transferred by means of electromagnetic waves. It's a little bit creepy to know this, but if you are sitting next to your fireplace in the dead of winter and you're warming up next to the fire, well, there's heat energy that is being transferred by way of convection, right? And that is going up your chimney, right? So you have the hot air molecules that are in contact with the surface of your fire, and that is causing the hot air to rise, and then cool air from the rest of your house is filling that back in. So that's not how you're keeping warm by the fire. Hopefully you're not warming up too much by means of conduction, because that would be like taking a metal poker and sticking it in the fire and heating up your hand that way. Why are you warming up by the fire? Radiation. It's the radiation, radiated heat from the fire that is warming you up. A little bit creepy. Going through this again, here's a couple of examples. Hey, we can put them all together. One application of conduction, convection, and radiation is the good old thermos bottle. So a thermos bottle will minimize heat transfer by conduction, convection, and radiation. Conduction, it's insulated. This is generally vacuum here on the outside. And so, and it's pretty good insulating materials, so that the hot liquid, I'm going to work with my tomato soup, I guess, my hot tomato soup here, will keep its temperature, because it's not going to lose heat to the outside environment by conducting the heat through the walls, because I have either air insulated or vacuum insulated region here, which is a very poor conductor of heat. So the hot stays hot and doesn't lose it to the outside. Convection, we have a cover on top that's made of a pretty good insulating material, a plastic cover with a gasket and all. So Not going to lose heat by way of convection because I keep the cover on. If I take the cover off, I will lose heat by way of convection. And then if you ever look inside a thermos bottle, you will see your weird eyeball kind of looking back at you because it's got a mirrored surface inside. Why is it mirrored inside? Well, it's mirrored inside to prevent heat loss by way of radiation. So the hot molecules, the hot liquid, will tend to emit radiation in the form of infrared radiation, and that mirrored surface reflects it back in rather than absorbing it and transmitting it outside the container. So if I had my thermos bottle with a black surface all in, it would absorb the radiated heat. If you notice your, I don't know, coffee mugs, coffee cups from Dunkin' Donuts or somewhere else, they're not black cups, maybe because that would look creepy, maybe that's marketing, but they're also white. Tends to be better reflectors of radiation, keep it warmer longer. All right, so some of the questions from the homework I just kind of have in here just so you can see where they fit in the context of the material. So here's some of the homework questions just in context. All right, I think this has gone on for a while, so I'm going to take a stop so that you don't get too bored with this.